Okay, good morning, everyone. So thanks for coming to revise redox. So today we are going to revise redox. We are going to first revise the rules in assigning oxidation states in particular. Now, you need to know what is oxidation state. Oxidation state is basically a concept that we invented to imagine what charge an element would have. Okay, so we are trying to imagine what charge it could have. Is it 2 plus, or is it plus, or is it minus? We're looking at charge. Of course, not everything has charge. For instance, if you are a covalent molecule, you share the electrons. If you share the electrons, then you will not be having a charge, because charge only forms when you lose or when you gain electrons. However, in covalent molecules, electrons are shared. Having said that, this is where this concept comes in useful, because we are trying to imagine, using some rules, what charge it might have, even though it's a covalent molecule. Okay? So we're going to start with the rules. There are basically only 3 rules. The first rule has to do with the uncombined element. So this is more of a definition, actually. By definition, an element is uncombined. It has not reacted with anything else. As a result, the oxidation state must be 0, because it's the most fundamental, it's the most basic form of the substance. It's not combined. It has not done anything to its electrons. Therefore, it should be oxidation state of 0. So good examples. These are your metals: magnesium, sodium, titanium. These are examples of metals. You know that they are metals. You can find them in the periodic table. At the same time, do you notice that they are not combined? The formula Mg, Na, Ti is not combined. Therefore, the oxidation state is defined as 0. Next, we have the molecules, but these are also elements: O2, Cl2, H2. They are not combined with other elements. They are just on their own. Oxygen with oxygen, chlorine with chlorine, hydrogen with hydrogen. Therefore, by definition, the oxidation states of these elements are all 0. Okay, that's rule number 1. Rule number 2 is more to do with the common oxidation states of certain elements in the compound. So in a compound means the elements have reacted together. Different elements have reacted and combined chemically together. So in a compound, oxygen is usually -2. Okay, this is by far the most important rule and the most commonly seen and applied rule. Oxygen is usually -2. The only exception to this rule, which I guess you can take down now, the only exception to this rule is if the substance, if the compound is called a peroxide. We will tell you it's a peroxide in its name. So if you read hydrogen peroxide, for example, if there is the word peroxide, the oxidation state of oxygen is -1. So that is the only exception to the rule that oxygen is -2 in its compound. The next important rule is hydrogen. Hydrogen in its compound is +1 oxidation state. Now, immediately you notice when we write oxidation state, the sign comes before the number. So this is also important. It's a convention. It's the correct way of writing oxidation state. The plus or minus sign has to come before, in front of the number. Okay? Now, so once we clear oxygen and hydrogen, which are very commonly seen, we come to the group 1 and group 17 elements. So group 1 means what? Group 1 elements means like sodium, potassium. Sodium and potassium, when they are a compound, right? For example, sodium chloride is a compound. How does sodium form a compound? Group 1, they lose 1 valence electron. When you lose 1 valence electron, the charge that you form is positive. That's why group 1, the oxidation state is +1, because oxidation state is charge. Okay? Group 17 is the reverse. Group 17 is like chlorine. Chlorine has 7 valence electrons. It gains 1 electron. When you gain 1 electron, therefore, you will develop a minus, a negative charge. Hence, the oxidation state of group 17 is usually -1 in its compounds when it reacted. Okay, now these are very, very useful. These four are very, very useful. So I strongly recommend that you learn them. But when you learn them, let's also learn them in this order. That means I will learn the rule for oxygen first. Then I will learn the rule for hydrogen, then group 1 and 17. The reason why I'm saying this is because of its usefulness. Generally speaking, there are very few exceptions to this rule. However, the very last rule regarding group 17, you need to know, actually group 17 could have other oxidation states as well, as we will soon see. All right. So the rules that will apply first are the oxygen and hydrogen rules. So it's good to learn them first. All right. And whenever you are deducing oxidation states, generally speaking, we are going to look for oxygen, hydrogen, group 1 first. Okay. Now, so we have cleared rule number 2, which is more to do with the common oxidation states of certain elements like oxygen, hydrogen, group 1, group 17. And finally, the last rule is basically how we calculate oxidation states. You need to know when we add up, when we sum up all the oxidation states of the atoms, it must equal to the overall charge on the substance. That makes sense. Oxidation state is this concept where we imagine there's a charge. If you add up all the charges, you sum all the charges up, it should add up to the overall, right? Charge. If not, it wouldn't make sense. Okay? So now we're going to do a few examples quickly. The first one is PbO2. So the formula of the compound is PbO2. You're going to ask yourself, what is the overall charge? The overall charge here, it must be 0, right? It's simply 0 because there's nothing written on the top of PbO2. It's not PbO2 plus, it's not PbO2 minus, it's just PbO2. This means that the overall charge is 0. Automatically, we start applying the rules. Oxygen is -2. By definition, oxygen is usually -2 in its compound, right? There are 2 oxygens here. If each oxygen is -2, 2 times -2 is -4, which automatically means Pb has an oxidation state of +4. Why +4? Because you need the sum of Pb and the oxygens to become 0. That means when you add the Pb and the oxygen oxidation states together, it must go to 0. It can only go to 0 if Pb has the opposite sign, which is +4 to balance out and cancel out the -4 from the 2 oxygen atoms present. Okay, so that's a simple example. Now we move on to the next one, MgCl2, which was also present in your notes. So how do you work out Cl's oxidation state? The way to work that out, of course, there are a few ways. The first way to do this is to realize that, hey, it's magnesium chloride. Magnesium, if you look at the periodic table, is in group 2. Then you got to ask yourself, okay, how will a group 2 element like magnesium react? How did it form MgCl2? Oh, it formed MgCl2 because it lost 2 valence electrons. Therefore, magnesium's oxidation state must be +2 because when you lose 2 valence electrons, you develop the double positive charge. So magnesium is +2 oxidation state in MgCl2. Okay? So now, clearly, if magnesium is +2, what will chlorine be? Remember the overall charge again, the overall charge, there is nothing written on the top of this compound's formula. So the overall must be 0. How do you go to 0 when you already have +2 on magnesium? Clearly, Cl2 must cancel out the magnesium's +2. Meaning Cl2 is -2. But oxidation states are for each atom. One atom. Over here, there are 2 chlorines. 2 chlorines together is -2. So each chlorine is -1. So the oxidation state of chlorine in MgCl2 is -1. Now, this is very important. You need to know that oxidation state is for each atom. One atom, okay? It's always defined based on one single atom. So over here, you have 2 chlorines, so you need to remember that the oxidation state of each chlorine is -1, okay? And finally, We have come to a more complicated example, KClO3. Again, you can see the overall charge is 0. There is nothing written on top of the formula, right? There's no plus, no minus. So KClO3 must add up to 0. So we are going to apply the rules again. And you notice the rules that I'm speaking about is always to do with oxygen and so on. So oxygen is a good place to start whenever you are stuck on a problem. Oxygen is -2. Okay? There are 3 oxygens. Remember, each oxygen is -2. There are 3 of them. So together, it's 3 times -2. Potassium, this is where the periodic table comes in. If you look for potassium in the periodic table, you will quickly realize it's found in group number 1. Therefore, potassium is +1 oxidation state. Now, this makes sense because potassium is group 1. Therefore, it will lose 1 valence electron to form K+, which is +1 oxidation state. Now, for such more complicated problems, it's useful to let your unknown be X. So in this case, chlorine, let's let the oxidation state of chlorine in KClO3 be X. What's the purpose of doing this? By doing this, I know that the equation must sum up to 0. And once you do that, it will simplify the whole equation to just, because 1 plus 3 times -2 is actually -5. You can use a calculator for that, and that will give you +5 for the oxidation state of chlorine in KClO3. Okay, now it's very important when you solve an equation and you get the positive number. Remember, oxidation state is the charge that something would have, right? Charge, if it's positive, you must still write the plus. The calculator is, of course, not going to give you the plus. It will just write 5 on the calculator. But you need to know the plus is important to show. Okay, so these are some examples. Then now let's move on to the examples with charge. So now there's charge. You can see that there's charge on the next 3 examples with bromine inside them. So of course, when there's charge, you know there is an overall charge. That means when you add, it must go to a certain charge. You realize that the charge is -1. Overall, that means you add everything up, it's -1. In the first example, Br minus, it must add to -1. That means the bromine is just automatically -1 oxidation state in Br minus. Because there's nothing else to add, it's just itself, right? Br minus. Now, Br minus is not an element. It's not an element. Many students get confused because they only saw the Br minus there. Then they are wondering, oh, it's not combined, right? But remember, how do you form Br minus? To form Br minus, you must have gained an electron. That means it gained an electron from somewhere else, someone else. Where did this electron gain come from? It could come from a metal like sodium, potassium, which has lost an electron. That's why when we write Br minus, what we are trying to say is this is part of an ionic compound with sodium, potassium, or some other metal that has lost its electron. Okay, so what you need to take away is, so long as you see a charge, right, it cannot be an element. It cannot be. It must be part of some ionic compound. All right. Now, so Br minus is straightforward because it's just -1. The charge is -1, and there's only Br, so it's -1. Okay. But how about BrO minus? Again, you apply your rules. Oxygen is almost always -2. So now, I have 1 oxygen, then I have bromine. Let it be X. It must add up to -1. Now you try solving this equation, you will get X equals to 1. Of course, you don't write 1, please. The sign is important. If it's positive, you must write plus. Okay, so X is +1. So the oxidation state of bromine in BrO minus is +1. Okay, finally, can I get you to work out for BrO3 minus? May I know what is the oxidation state of bromine in BrO3 minus? Okay, let's work it out and let's take about 1 minute to do that. Once you're done, the Q&A function is there. You can use the Q&A function on Google Meet to type in your answer for this particular question. Okay, so let's start now. Okay, I've received one person who wrote in the answer. How about the rest? Are we working it out as well? Okay, the rest, I hope you are working out the oxidation state of bromine in BrO3 minus as practice, because you will need to practice before we go on to the writing. Okay, so in the interest of time, let me just review the answer. Okay, the oxidation state of bromine in BrO3 minus is actually +5. All right, so if you didn't get +5, then we will need to relook at where in your working have you gone wrong in the calculation. All right, now calculating oxidation states is just the first step towards answering the question for redox. Now, what does the question for redox almost always look like? The question for redox often involves explaining. So for instance, explaining what? So we will give you an equation resembling this one. This equation is also inside your notes, all right? Now, this equation will be given to you, but then they will ask you, determine, deduce, explain what has been reduced and what has been oxidized using changes in oxidation states. So if you are faced with this equation, where do you begin? The answer is you always begin with the metal, always. All right? If there is a metal, we start with the metal. So in this case, the metal is zinc. You will quickly be able to work out that, hey, zinc at the very end, it's not combined, it's an element. The formula says that it's just Zn. It's not combined with anything, so it's 0 by definition. We are applying rule number 1, oxidation state of an uncombined element is 0. Over here, zinc is +2. I'm able to work that out because I know that oxygen in a compound is -2. Since zinc oxide, ZnO, does not have any charge, that means zinc must be +2 in order to cancel out the -2 and so that it will sum up to 0. Now, so once you have worked out the metal, you can quickly see that the oxidation state of zinc has decreased from +2 in ZnO to 0 in Zn. A decrease in oxidation state means reduction has taken place. It's reduced. Now, there is a 2 in front of the ZnO. The 2 in front is only for mole ratio. This means that the 2, this one, should not appear in your redox answer because it doesn't affect your redox calculation. It doesn't affect what is reduced and oxidized. It is wrong to say that 2ZnO is reduced. It's wrong. The correct answer is just ZNO is reduced. Now, this I'm highlighting this because I did see this a number of times inside what y'all wrote. It's very important to realize when you use the tool, the number in front of a chemical. Okay? So the number in front of a chemical is for mole ratios only. It doesn't affect the redox. Therefore, it should not appear in your redox answer to explain what's reduced and oxidized. Okay? Now, I'm just going to quickly write out the answer so that you can see the format. I believe many of you already know the format, so I think you should be fine. The only thing I want to highlight is, please spell the element's name out. So ZNO is reduced as the oxidation state of zinc decreases. You need to say whether it's an increase or decrease. You cannot say that it changed. It's decreased from +2 in ZNO. It's very important to say where, because if you don't, it's not immediately clear. Okay? Now, the redox explanation is often very standard. You must try to follow this format 100%. Okay? Please do not deviate, because when you deviate too much from this, many a times you miss out certain key points that I've highlighted and underlined in this particular answer. Okay? So we always start off by calculating oxidation state of the metal, simply because the metal is very useful in allowing us to deduce what has been reduced or oxidized. Okay? Next, after the metal is done, we move on to the non-metals. Non-metals like carbon, nitrogen, chlorine, these are examples. Okay? So carbon is next. Again, you can see element at the start. It's just C, right? Element is 0 by definition when it's uncombined. It's not combined with anything. At the end, it forms CO2, carbon dioxide. So again, we apply the principle. Oxygen is -2. However, there are two oxygens. Notice how the number at the bottom affects your redox. The number in front does not affect the redox. Number in front is for mole ratio. Number at the bottom indicates it's bonded together. We are sharing the electrons together. Okay? So the number at the bottom has a different meaning. CO2 means the two oxygens are bonded together with carbon. They have shared electrons together. So that will, of course, impact the oxidation state. So carbon in CO2 is +4. And with that, it's very straightforward. Again, I will just quickly write the answers. Okay, so again, spell out the oxidation state of carbon increases from 0 in C to +4 in CO2. Okay, so it's very important to say where. Okay, so I think these you should be quite familiar with. I think it's just a matter of practicing to ensure that you know the format. Now, for practice, I've put two other questions below. Okay, okay, I'll just scroll down to the questions in a while. Okay, so you can see B and C below. My advice for those in the Google Meet is to now try writing them on some paper. Once you are done, okay, you can just take a picture of it and then send it to me for me to check and verify that you have gotten it correct. Importantly is the format. I believe most of you can calculate oxidation states by now. It is just the format of the answer has to be correct. So let's take about 4 minutes to work on B and C. Once you're done, you just take a picture of your writing to show me and for me to check. Okay? Okay, maybe we take 2 more minutes to finish up B and C. For B, like I said, if you started with the metals oxidation state, probably you will finish it much faster. Same with C. For part C, there are two metals there. So if you work their oxidation states out, you would be able to finish it much more quickly as well. Okay? I hope the rest are also practicing because it's very useful to be practicing the writing. Okay, I'll just quickly write out the answer for part B so that you can take a look. Okay, for those who send me your answers, I think it's broadly speaking correct. Okay, it is just that again, like I said, you must not miss little out. It's very important to ensure that you really specify. So, like for example, Zn is oxidized. Those who sent me, you all got it correct. But how you write it is important as well. Okay, most of you also got the oxidation state correct, but you need to say it's from 0 in Zn to +2 in ZnCl2. You need to specify where you are referring to, or else it's incorrect. All right? Please, please, please ensure you do that. Okay? I've seen many of you actually you got the oxidation states correct, but I'm unable to give you the mark because you need to say where is it, like 0 in, +2 in. All right. Now, once you have that, you will realize that you can proceed very quickly. Now, after zinc is done, the next step will be to do either hydrogen or chlorine. Now, I will do hydrogen simply because I realize that hydrogen at the very end is an element, it's 0. All right. and hence it's much more quick for me to realize that HCl has been reduced, okay, as the oxidation state of hydrogen decreases, all right, from, again, +1 in HCl. It's very important to say +1 in HCl to, at the end, it's an element that's not combined, so it's 0 in H2. All right, so little things do make a difference. Okay, now for part C, let's try doing it now. For those who have not done it, I'll quickly do it and let me see the answers. All right. Okay, so like in part C, my biggest hint, or not the biggest hint, but really a tip, always focus on the metals where they are present. So like magnesium is a metal, Cu is copper, copper is a metal. It's very important to always do the metals. Okay, very often in combined science especially, the equations that we give you will often include metals, and it is the metals that change their oxidation state, whether it's an increase in the oxidation state or decrease in the oxidation state. So the metals, right, will definitely lead you to the answer. Okay. Now, some of you have begun to ask about oxidizing and reducing agents. Indeed, all right. Once you have worked out what is reduced and oxidized, actually, it's very easy to work out what is the reducing and oxidizing agents, which we'll come to in a very short while. All right. Now, for part C, let me just quickly write out the answers as well. Okay, then you can check against my answers to see whether you've gotten it correct. Always start with the metal. Okay, so I will start with magnesium, for example. Mg is a metal, right? So I will start with the metal, Mg in this case. So you will realize that Mg is oxidized. Okay, notice how I use the formula Mg is oxidized as the oxidation state of magnesium. So you must spell the element's name out when you talk about its oxidation state. And please avoid saying its oxidation state in your answer. You need to specify, be detailed. Oxidation state of magnesium, spell. All right, it increases, okay, from, again, don't make the mistake of just saying from 0 to +2. It's from 0 in the Mg. Where is it? 0 in the Mg, +2 in the MgCl2, okay? This is how we present a good answer. Next, we move on to, of course, Cu. Cu is the other metal, so that's copper. So if you see at the very start, Cl minus 1, Cl minus, therefore Cu is +2. Remember, the plus comes before the number. Therefore, we can conclude CuCl2 is reduced. Now, you could also conclude this because you know that this is redox. In every reaction, there must be one reactant which is oxidized. If Mg is oxidized, automatically the other reactant, which in this case is copper 2 chloride, CuCl2, will be reduced. That's why it's redox together, right? So CuCl2 is reduced as the oxidation state of copper decreases from +2 in CuCl2 to 0 in Cu itself. Okay, so the answer should resemble this. Now, We'll move on from this. Once you have gotten this, it's 2 marks already, right? Now, the question might ask you not just what is reduced and oxidized, they might also ask you, what is the reducing agent? What is the oxidizing agent in this reaction? How do you work that out? Now, you must remember, reducing agent means it's an agent that reduces other things. It causes others to be reduced. So in this case, if we just focus on part C alone, CuCl2 is reduced. Who caused it? Who caused CuCl2 to be reduced? CuCl2 did not cause itself to be reduced. CuCl2 must have been reduced by something else. And the something else, of course, is magnesium, right? Magnesium caused the reduction of CuCl2. So magnesium is the reducing agent. You just need to add this on to your sentence just now. And that will answer the question, what is the reducing agent? When do you need to add this in? You need to add this in when the question requires, states for you to determine what is the reducing agent. So you must read the question. Is the question asking you what is reduced and oxidized? Or is the question asking you what is the reducing agent? And you need to tailor your answers accordingly. But it's based on the same concept, same method. The method is, let's calculate the oxidation states. Let's see how the oxidation states increased or decreased. Let's determine what is oxidized and reduced first. Because once I determine what's oxidized or reduced, I will know immediately what is the oxidizing and reducing agent as well. So because Mg is itself oxidized, we also can conclude Mg must be the reducing agent. So the idea is the reducing agent is itself oxidized. I am myself oxidized. That's why I can reduce other people. Okay? So same here. What is the oxidizing agent? CuCl2 is the oxidizing agent. Why do I deduce that? Because it is itself reduced. Anything which is itself reduced will be the oxidizing agent. Okay? So this is good to know, and good to know when to do what. It's always stated in the question. That's why reading the question is very, very important. Okay? Now, so since we are on this topic of reducing and oxidizing agents, how do we test for reducing agents and oxidizing agents in the lab? There must be a good, simple way to see whether something unknown is a reducing or oxidizing agent, right? So this is where we will test for reducing agent and also test for oxidizing agent. Ra stands for reducing agents, OA stands for oxidizing agent. Now, to test for reducing and oxidizing agents, we have different tests. It's just like QA. Remember, to test for carbon dioxide gas, you use lime water. When you wanted to test for ammonia gas, you would use a piece of moist red litmus paper. So same here, the test will be different, right? So to test for reducing agent, we add acidified potassium manganate 7. Okay, so the test to see whether something is a reducing agent is to add acidified potassium manganate 7. If the unknown substance is a reducing agent, then the acidified potassium manganate will change from purple to colorless. Color change from purple to colorless. Okay, so this is very important. You will need to know how it's like QA test. You will need to memorize. If it's a reducing agent, it will change the color of acidified potassium manganate 7 from purple to colorless. Okay, now the chemical formula of potassium manganate 7 is KMnO4. Okay, Okay, so it's a test for reducing agent. Okay, so what are the common reducing agents we have? Metals are common reducing agents. For example, sodium metal, the metal itself. Magnesium metal, the metal itself is a common reducing agent. Now, another common reducing agent that we use very often in the lab is actually a gas. Sulfur dioxide gas. SO2 gas is a reducing agent. One last one, which is what we said, hydrogen peroxide is also a common reducing agent found in your laboratory. Now, at the start of the lesson, I said something about peroxide. If you recall, peroxide is a special word. When you read this word peroxide, alarm bells should sound in your head. Peroxide means the oxidation state of oxygen is no longer the usual -2. Hydrogen peroxide. Peroxide, this word tells you it's -1 for oxygen's oxidation state. Okay, so this word peroxide, whenever you read this word, alarm bells should sound in your head to tell you that, hey, this is the exception to the rule that oxygen is -2, because in peroxides, like hydrogen peroxide, oxidation state is -1 for oxygen. Okay, so that's the test for reducing agent. To see whether something is a reducing agent, we add potassium acidified potassium manganate 7, and the color change, if it's a reducing agent, it will be from purple to colorless. Now we move to oxidizing agent. We will also add something. Sadly, that something is also a potassium compound, so you will need to remember. We will add acidified potassium iodide solution. All right, we'll add aqueous or solution of potassium iodide. So potassium iodide is a test for oxidizing agent. So if the unknown is an oxidizing agent, that means your unknown substance that you added potassium iodide to, the unknown is an oxidizing agent, then there is again color change. That's how it works. You can see a color change, that's why you know it's there. It's from colorless to brown. So you will need to know the color changes as well. So in the test for oxidizing agents, you add potassium iodide solution. If it's an oxidizing agent, it will change color from colorless to brown. Now, what are the common oxidizing agents we have in the lab? Very often, it's your halogens. Halogens meaning fluorine, chlorine, bromine. Okay, these are the common oxidizing agents in the lab. For example, chlorine gas is Cl2. Cl2 is an oxidizing agent. We can test that easily by bubbling into potassium iodide solution. It will change the color from colorless to brown. This shows you that Cl2 is an oxidizing agent. Now, another common oxidizing agent is actually a familiar sounding chemical. It's hydrogen peroxide. Hydrogen peroxide is interesting because you notice, hey, didn't it appear twice? It appeared once just now as a reducing agent. Now it's going to appear again as an oxidizing agent. So peroxides are interesting because peroxides can display both reducing agent and oxidizing agent properties. All right. So hydrogen peroxide or peroxides in general could actually function as a reducing agent as well as an oxidizing agent. It just depends on what it reacts with. Okay. So of course, this means that hydrogen peroxide will be able to demonstrate color changes with both acidified potassium manganate 7, where it's a reducing agent, as well as color change with potassium iodide. But in that case, hydrogen peroxide is the oxidizing agent. Okay, so hydrogen peroxide is both. So you need to know the test for both reducing and oxidizing agents well, just like you know the QA test well. In fact, this could very well be also in the practical, where you do QA at the same time you also do this. Okay, so these color changes, as well as which is the test for reducing agents, which is the test for oxidizing agent, must be learned well. All right. Now, so summing up the lesson today, we started off by going through the main rules, how to assign oxidation states. After finishing the rules, we went through the format of explaining what is reduced and oxidized. So please look through the format once more. How do you write the answers? Then we moved on to how to deduce whether something is a reducing agent or something is an oxidizing agent. Remember, reducing agent is itself oxidized. So just now in part C, Mg is the reducing agent because Mg is oxidized. The oxidizing agent must be itself reduced. That's why CuCl2 is reduced, hence CuCl2 is the oxidizing agent. And now we are ending off the lesson by going through the test, the laboratory test to tell if an unknown substance is a reducing agent or oxidizing agent. You must know that acidified potassium manganate 7, KMNO4, is a test to see whether the substance is a reducing agent or not. The test for oxidizing agent to see whether something is oxidizing agent is to add potassium iodide solution to it. Okay, and something interesting, some examples of reducing and oxidizing agents are shown there. Something interesting, which is also in your notes, is that hydrogen peroxide is both a reducing and oxidizing agent. It just depends on what it reacts with. Okay, Ken? So that brings us to the end of today's consult. Now, for those in the Google Meet, please stay for a while so that you can ask some questions if you want to in the Q&A. If not, I will stop the recording now. Thank you. Let me just stop the recording.